SwayamPrabha. Digital India. Educated India.
So far we have been looking at some of the fundamentals of Lyapunov theory, some preliminary background and some physical insights into how Lyapunov has come up with different theorems, and we saw some kind of a intuitive understanding about it. Okay, so if you recall, we had seen these stability proofs based on some definition of some functions which are energy based functions, and their derivatives along the system trajectories. Okay, so we defined some mathematical preliminaries and come up with this idea which what Lyapunov has come up with. Okay, and now we'll see more formally some mathematical kind of stability theorems. We'll not get into the proof of them, but we'll just see the mathematics a little bit more in detail and apply it to the case of development of control, and providing the proof for stability proof for any control that is proposed. Okay, so that process we'll go through. Okay, so let me get to the slides now. So see, this first theorem we will just recap that we saw was about the stability. Okay, so stability of a system. So we are considering this system which is x dot is equal to f of t comma x, where x is a state. X is a, so if you have n state system, okay, typically say if you take a 2R manipulator robotic system, that robotic system would have 4 states. Okay, 2 degree of freedom typically will have 4 states. So that kind of a system if we have, then this x will be a 4 vector. Okay, so 4 by 1 kind of a vector. Like that, f will be 4 by 1 kind of a vector. Okay, and it's a function of so it takes r and rn and r to space rn again. Okay, so that is how this f is defined. Now for this system, this first stability theorem says that the equilibrium x is equal to 0. Okay, this is a x vector, 0 vector of a system is stable if there exists this is now locally positive definite function C1. Okay, C1 means continuously differentiable at one time, and locally positive definite function we have seen what are the definitions of that. So LPDF C1 function, which is like typically designated as V. Okay, so V is like Lyapunov function, some function. Okay, if it satisfies this property LPDF and C1, then we call it Lyapunov function candidate. Okay, this V is Lyapunov function candidate if it is satisfying these properties. Okay, so this V is taking R plus, means is a time positive value to and Rn to R space. Okay, so this is a real valued function. This is a LPDF function V and constant small r greater than 0. Okay, so this is defined to have some kind of a finite radius, ball of finite radius r here. So we are defining a local definitions here. We are not kind of considering like a global stability of a system. We are considering local stability of a system. So it is sufficient to have these properties hold true in small kind of a hyperball of this radius r. So when this v dot of this function, okay, which is Lyapunov function candidate, v dot is less than or equal to 0. Okay, so and this should be valid for all t greater than 0 or greater than t0 and within this ball of radius r. Okay, x belonging to this ball of radius r. Okay, and v dot is a function which is again real valued kind of a function, is evaluated along the trajectories of a system. Okay, so trajectories of a system, you remember, like, you know, v dot will be actually del v by del t, plus del v by del x into x dot. Okay, so this is like, you know, typically given as expression for v dot. So we have seen what is this derivative along the trajectories, and where this x dot is substituted as this function here. Okay, so we'll see through some examples how this is done and all those processes, but this is how this stability theorem is defined. And if this is valid for like entire Rn space, then it becomes like a globally stable system, and there this also needs to be valid entire Rn space. Okay, then you have this notion of asymptotic stability we have seen. So now this is a asymptotic stability theorem for so we need now, you know, we say for the same system, same equilibrium is uniformly asymptotically stable if there exists C1 decrescent. Now this is a decrescency is additional property that is put here. Okay, so decrescency is this upper bound by class K function. Okay, and then you have this LPDF, these conditions are same, such that minus v dot is an LPDF function. Now this is not just less than or equal to 0, that equal to sign is not valid now. It is this needs to be strictly like, you know, a locally positive definite function minus v dot. Okay, so it can be 0 only at 0, no other point it can be 0. But in the previous stability definition, this was lesser or equal to 0 kind of a sign. So now we want v dot to be strictly less than 0 for asymptotic stability. Okay, so this is a more stringent condition. This is one kind of a condition, decrescency, and then there is other stringent condition, LPDFness. Okay, so this is how, like, you know, this theorem comes up. So we will not, again, as I said, we will not get into the proof of this theorem, but we are more interested in the application. There is an entire different course can be given on about, like, you know, theory and its proofs, and you know, all the mathematical nitty-gritties and details about the Lyapunov theory for utility in many different applications. What we are looking at is their application in the mechatronic systems alone right now. So let's say with the example. Okay, so we have this example of you want to control this mass which is resting on the surface and applied by the force F. This force F is considered to be a control force. I can change it, you know, whatever way I want it to be changed, and we want to know, okay, what is this force, if it is specified like say in this case like a PD control, then whether this is going to stabilize my system or not. That is what my interest, and I want to use Lyapunov theory to prove that. Okay, so to say, whether it is asymptotically stable or it is stable, or what kind of a proof I can get. Okay, that's what I want to know. So what is the equation that is governing the system dynamics is mx double dot is equal to F. Very simple. So this is a two-state kind of a system. In terms of, like, you know, if you want to see it in terms of x dot is equal to f of t comma x, you can convert the system into that form by saying x1 and x2, where x1 is equal to x and x2 is equal to x dot. So x1 dot will be equal to x2 and x2 dot will be equal to f by m. So this is how I can define that system. But I can also work with, see, for such a simple systems, we can directly work with this basic system itself, and understanding that, okay, our state has x and x dot. Okay, so your the system can be transformed into the error equation by considering like xt minus c. We want to take the system to xt, so xt minus x is a error, and then we can convert this me double dot is equal to f will be the new system. So like that you do like a lot of this little bit of you know, in intermediate steps to see that, okay, me double dot is finally your equation f, and f is defined in terms of E as kp times E minus kd times x dot is also if you write x is equal to E is equal to xt minus x, okay, then x dot becomes equal to E dot, rather E is equal to x minus xt, okay, that's what you need to write, okay, then E dot will become equal to x dot. So these small nitty-gritties are there to be worked out and see for yourself, okay. Then now for such a system, if we define Lyapunov function candidate, okay, so typically for mechanical systems we resort to the energy of total energy of a system as a indicator of this Lyapunov function candidate. It is not a must, but many times it works very well, okay. So given some system, you try to see in terms of this control and in terms of system dynamics, what is total energy of a system. For example, here we know that for this system half m x dot square will be its energy of this mass, okay. In terms of it will be half m E dot square. This is the first term in this V, and then we will have this potential energy coming up, because this proportional control here is acting as if we are connecting a spring here, okay. So the spring potential energy is Kp times E square, okay. That's what we are doing, this Kp when we put, then we are kind of putting a spring which is getting deformed by the value of the error, and that spring will have this E will be 0 when this mass reaches the final value, okay, xt. So like that, this term comes from the proportional control term. So you will find this term, you can take it similarly for many other kind of systems as well. When you are using proportional control, you can take this half Kp E square as a term for the energy corresponding to that proportional control, okay. So this is becomes like a total energy. Now this can be verified to be locally positive definite function, okay, by applying all the different conditions that we had put for locally positive definiteness of a function. So it has both E dot and E, both the states are coming here, and that's why this is like a locally positive definite function. I mean, it's actually a globally positive definite function with respect to E belonging to R2 space. Then we differentiate this to get V dot, and then we get this E double dot here. Now this E double dot is to be substituted from the system dynamics equation here, and whatever control choice that we have. So this m E double dot will become Kpe. So this is x double dot is nothing but E double dot is equal to minus Kpe into Kd E dot. X dot is also same as E dot. Okay, so this E double dot is substituted here from the system trajectories. M E double dot is this value, and then we substitute that and simplify. You get V is equal to minus Kd is E dot square. Now this is not having any term corresponding to E. That's why this is less than or equal to 0, not strictly less than 0. Okay, so that's why we can conclude that this this control, PD control, gives this system stability. Okay, only we can say the system is stable, or this equilibrium x is equal to xt is a stable equilibrium. It is not asymptotically stable. Okay, this is important here. See, with this we cannot get it is to be asymptotically stable. But is it that this system is that way, that only E dot is going to 0 and E cannot be going to 0? No. We know from the linear system analysis and our actually perfect solution that both E dot and E are going to go to 0 when the PD control is applied. Okay, so then but Lyapunov theory is not yet able to establish that. Okay, so this is how we can look at these results. So Lyapunov analysis is not saying that it is not asymptotically stable. It is just saying that it is stable system for now. Okay, for asymptotic stability we need to do something more to prove. Okay, and remember again, these rules of the Lyapunov theorem are only the sufficient conditions. Okay, so then if these conditions are satisfied, then you say the system is stable. If they are not satisfied, that doesn't mean anything. Okay, you cannot conclude nothing about that. If these conditions are satisfied, then you have this result available. Okay, so this is very important thing to know, that okay, because you are not able to find out any V which will satisfy these conditions, that then the system is not stable, or you cannot conclude that otherwise result. Okay, these are only sufficient conditions. Now we can apply this to entire domain of this mechanical systems, so to say, which are obtained by using our Lagrange formulation applied to fully actuated mechanical system. Okay, mechanical system, I mean the rigid body mechanical system. We restrict our discussion to rigid body systems alone. Although some parts can be extended to flexible bodies also later, but right now for this course, let us focus on only the rigid body systems, multi-body systems, and fully actuated systems. Okay, so number of degrees of freedom are equal to the number of actuators in the system. Okay, so so this was the equation, if you remember, that was obtained by the Lagrange formulation, and we introduce the motor dynamics into it. Okay, so motor dynamic equations, if you remember, they are also in this form, but now this torque K, okay, or this is kth joint, whatever we are considering here, this is actually coming from this equation, or this is what is a connection between the Lagrange formulation, which is giving us the external force in the generalized in the direction of generalized coordinate as torque, will be provided by the motor. Okay, so this is coming as a load torque on the motor dynamics. Okay, so with this some kind of a gear reduction here. Okay, so RK is some kind of a gear reduction. Okay, so theta, this is theta is a motor angle, and then these are some of the motor parameters, and this model can be incorporated through this kind of a connection, tau K. Now this tau K, if you substitute from this, you get some simplification here, and you get some kind of a equation. Okay, or we can convert this motor dynamics also into so this theta m can be substituted by 1 over RK into QK. Okay, as a so everything will be in terms of the generalized coordinates of your Lagrange formulation that we have found out, and this tau K can be substituted here, and now everything becomes into the generalized coordinate QK. Okay, and this equation will look something of this sort. Okay, so this has some kind of a complications coming up here. Additional kind of inertia terms are getting added, and that's what is happening to this equation here. Now in the matrix form, these equations will finally look like this. Okay, so this entire thing can be put into some kind of a matrix vector form. Okay, then it will it looks the complication that you usually get by using this Cijk kind of a terms, and this is kind of gone here. Okay, so you see that, okay, this is one kind of a n by n matrix, where n is the degree of freedom of the system, or n is number of actuators in the system, same fully actuated system, and you get this D matrix little bit modified because of the motor parts coming in, and then this U vector is basically all the inputs to the input voltage to the motor, which is defined this way. So V is actual voltage going to the motor, but this constant is getting multiplied, we get our U, okay, or control input U in the actuator, that is represented as a vector up here. Then this G vector is coming, B vector is coming, and then C was a big many different terms here that will be kind of collected in some kind of a matrix form. C, Q and Q dot, C is a function of Q and Q dot multiplied by Q dot here. Okay, so this D plus A is similar to our inertia matrix kind of a term here. Okay, so now this So these one can have another approximation to this system by saying that okay, you have the motor equation alone, but all the terms which are coming on the motor equation, you remember the motor equation was something of this sort. Okay, here is a motor equation, okay, in terms of theta and in terms of this. Now this can be considered as a disturbance, and we can directly write some control here. That is another kind of a possibility that can exist if you want to avoid or we are not interested in too many very high performances in the robotic system or mechanical system. Then we can do that okay, we are just kind of considering this as all the nonlinearities as a motor as a disturbances, and then collect them all together as these dk terms. Is nothing but this tau k term, okay. And we can use linear control on this equation also, okay. But right now we are interested in doing some nonlinear analysis with this equation, okay. Now we want to see that okay, we propose this PD control, okay, on the joints. Okay, so Q is a generalized coordinate in terms of typically if it is a n degree of freedom robot, it will be the robot joints, okay, or generalized coordinate. So in the direction of generalized coordinate, you define this U where Kp and Kd are matrices. They are kind of typically diagonal matrices. And Q tilde is defined as Qd minus Q, okay, here. So desired kind of a generalized coordinate minus actual generalized coordinate, okay, that is the error term that we are defining here, okay. So this U is equal to Kp times error and Kd times error dot is what we are defining here, and these are now in the vector matrix form. So this U is again a vector which is used here, okay. So this U is here, and now we are interested in looking at how do we do this analysis using Lyapunov analysis, okay. So what is to be proposed as a Lyapunov function candidate here? Can you think about that? Okay. So see what we did for the simple kind of a mass resting on the surface. We used some kind of a energy based Lyapunov function. Now we can think of on the similar lines. Okay. So what is the energy of such a system where you have fully nonlinear dynamics of n degree of freedom robotic system happening here right now, okay. So this kinetic energy of this is based on the d jk terms or d matrix in this equation, okay. So this will give you kinetic energy, okay. So typically the kinetic energy will be given as q dot transpose this D matrix. Now we have an additional term coming from the motor inertia also, and Q dot, okay, Q transpose dq, okay, Q dot transpose dq dot will be your kinetic energy, and the potential energy term similar to the potential energy that we defined for this for the proportional control, okay, considered as a spring. We have now, because this is a matrix form, this is Q tilde transpose Kp times Q tilde. That will be the total potential energy corresponding to all the variables or all the errors Q tilde. This is a vector here, this is a matrix, and this is again vector. Okay, so first term here is a kinetic energy, and the second term is accounting for the proportional feedback in the form of a spring elastic energy. Okay, so now we have these terms corresponding to Q dot also and Q tilde also. Now this can entire be converted into Q tilde alone by using this relationship Qd dot minus so Qd is say a fixed quantity. We want to go to a fixed desired position, okay. So we consider for this discussion right now that Qd is not a function of time, it is a fixed point where we want to go, okay. So this is a, as we saw, this is a regulation kind of a control, not a tracking control, okay. So for this Qd is constant, so Q tilde dot will be equal to minus q dot. Okay, so that's what we can do here, substitute for this here. Okay. Now if you see this time derivative of v, so we can use this q tilde according to, like, wherever we need. So finally it is right now kept in q dot terms only. Okay, so now time derivative of v, if you see here, if this is a v, like, can you write the expression for time derivative of v? Just try it out. Okay, pause here, try it out, and then, like, proceed. So it will have these terms which are derivative of these times this plus this times derivative of this. So this is like a chain rule that we are applying here. Okay, so this chain rule, when you apply, what is the derivative that results here is this. Okay, so this is q dot transpose dq plus j q double dot here. So first derivative of this term is taken. Okay, and then half q dot transpose d dot q. Okay, and then there will be a term which is same as this term, so this half will actually go away. Okay, so this half should go away here. The way you have this q dot transpose kp q tilde. Okay, so here also this q tilde dot transpose kp q tilde is coming, because half will be gone, because, like, q tilde transpose kp q tilde and q tilde okay, q tilde dot transpose kp q tilde and q tilde transpose kp q tilde dot. Okay, these both are going to be same terms, and they'll add up together, and you will get this half cancelled out. Okay, and so you can see this negative sign will come based on the transformation between q tilde and q dot. Okay, q tilde and q actually, or q tilde dot and q tilde. Okay, now solving for this, we know that now from the equation of dynamics here, that dq plus j q double dot, this part of the term will be equal to this whole thing shifted on the other side and substituted for u. Okay, you will get this term here as u minus c q of q and q dot times q dot plus b q dot. Okay, now we are setting gq to be 0 here for this discussion right now. Okay, so we can add, and, like, we will have some compensation to be done in control for that term. Okay, but right now we will not worry about that term. Okay, to make our first understanding easier here. Then you have this term. So this is this half is not there, so I have not put that half here. So you get this term first, then this term as it is, and so you have derivative of d happening here, and then here you will have this same term coming up here. Okay, now if you see that we collect these terms in a very specific manner. Okay, what we do, see, still we have not used u here, u is kept as it is, and then this bq dot term. Okay, and kp q tilde. Okay, so this c term is moved out of this place. Okay, so this c term is taken out, and this kp q tilde term is put here in. Okay, and here like u minus this c q dot minus b q dot, this should be minus sign here. Okay, so that's why this will become minus bq. Then you use this d dot minus 2c term here. This 2 is coming because this is half outside here. So d dot minus 2c q dot, and then q dot transpose. Okay, so we are collecting this term here for a reason, because we know that d dot minus 2c is a skew symmetric matrix. for the mechanical system, as we have seen in Lagrange formulation, and that's why this is quadratic form will yield 0 here. Okay, so we do that and we get this expression for B dot as Q dot transpose U times B Q dot and minus Kp into Q tilde is coming. Now you propose this V is equal to Kp into Q tilde minus Kd into Q dot and substitute it here, we get this expression here to be this. Okay, V dot is equal to minus Q dot transpose times Kd plus B Q dot. Okay, so this remember this Kd is a diagonal matrix, B is a damping matrix in the system, that also can be a diagonal matrix here, and then you get this final expression. Okay, and this is again has only Q dot kind of a terms here. So if you see this these relationships happening are exactly similar to what is happening in the scalar form for our simple mass on the surface kind of a system. Okay, so again we get this is less than or equal to 0. Okay, then because there is no term corresponding to Q, so for some values of Q, this Q which is non-zero, this term is still going to be 0. Okay, so if Q dot is equal to 0. Okay, so that means it is violating this PDFness of minus B dot kind of a term. That's why this is less than or equal to 0. Okay, so so this Q dot will be this condition we can make Q dot is equal to 0, but Q is not equal to Q desired yet. Okay, so this is not proven yet. So Q dot is equal to 0 means Q tilde dot also will be equal to 0. Okay, so this to prove this we need some more kind of tools. Okay, so this equation is giving just a stability in the sense of Lyapunov and no asymptotic stability here. Okay, so we need some additional tool, and that tool is basically Lasala's theorem. Okay, what is this theorem telling us is given here. Okay, so this suppose the system x dot is equal to f of x is there. Now see the t is removed here, so this system is autonomous. Okay, there is no explicit time dependence happening here now. Okay, so this system is x dot is equal to f of x only, and there exists this function. This is again our Lyapunov function candidate, and this V is PDF and radially unbounded. So there is a new property coming here for this thing, it should be PDF and radially unbounded, and then B dot is less than or equal to 0. Okay, as we are getting in this case here, that B dot is less than or equal to 0 for all t greater than 0, and such that this x belongs to Rn space here now. Okay, for all R it is for all x it is valid. Then we define this set R here. Okay, how this set is defined? This set is defined such that x is belonging to this Rn space, and for all t is equal to 0 v such that v dot is equal to 0. So this x is such that v dot of t comma x is equal to 0. Okay, so this is how this set is defined. So we look at this v dot is equal to 0 condition now. So v dot is equal to 0 condition now we need to look at. Okay, so v dot is equal to 0 condition means like q dot is equal to 0. Okay, so we look at this q dot is equal to 0 condition and see that x is belonging to this Rn space, or this q or this x is belonging to this Rn space such that v dot of x comma t is equal to 0. Now this x is nothing but q in our case now. Okay, so we'll see with the example later, but understand that okay, we put this condition such that v dot is equal to 0 and x is belonging to this Rn space. Okay, so we collect all such x together and observe them. Okay, and this such all this x or this set R does not contain any other trajectory of the system other than the trivial trajectory x is equal to 0, then the equilibrium x equal to 0 will be a globally uniformly asymptotic stable system. Okay, this is what is Lasala's theorem saying. Okay, so this theorem is what we need to make use of in our case. Okay, So for PD control, we apply this theorem. If we see that v dot is equal to 0, like means like v dot is this is equal to 0, that means like q dot is equal to 0. Okay, then q double dot when q dot is equal to 0, I differentiate it once and I say that q double dot is equal to also 0, and this is because this q dot is equal to not instantaneous, it is for all time. Okay, so we need to see that, okay, for all time t is equal to 0, v dot is equal to 0. Okay, that is a condition that is coming. So then I see this in the system equation. Okay, so in system equation, wherever q double dot is there, I put that to be 0, and wherever q dot is there, I put that also to be 0, and then what remains is this control term here. Okay, and in that q dot again, this is equal to 0. So this means that kp times q tilde is equal to 0. Okay, and this implies that our q tilde should be equal to 0, and q tilde is like the error between the desired and actual trajectory. Okay, so this is how we establish, like in the full mathematical sense, that PD control indeed will take position and the velocity both to the final desired kind of a value. Okay, so this Lassalle's theorem implies that then the system is asymptotically stable, and this is what we make sure that our system is taken to the final position also, and final velocities are also to be desired value, which is 0 for the final position. Now when the gravitational term is there, then we need to compensate for that term. Okay, because it is dependent upon the g of q means it is dependent upon generalized coordinate. That term can be computed and compensated for by the control. So you do this control computation and you introduce this term in control to compensate for that. Okay, so this is u minus, if you without compensation, it will come like this here. Okay, so in u, if suppose there is a term which is g of q, then that will get cancelled out. So we can have all the terms that were there in the u before, this kp q tilde minus kt q tilde, plus now there will be a g of q term coming up here. Okay, and if that term is added to my u, then this will compensate for that here in the v dot, and again v dot expression will become similar to what we had before. Okay, so this is how we go ahead and handle that. Okay, so overall conclusion is that PD control can asymptotically stabilize a general rigid body mechanical system. This is very important kind of a conclusion here. So if you use simple PD control on many systems, they are fully actuated, it will work. Okay, it will take the system to its final value. In the presence of gravity, if there is a gravity compensation to be done, that you do that, and then this PD control will work. Okay, so even without having all these kind of analysis, one can definitely control any rigid body mechanical system, okay, fully actuated, by just using PD control, and it should work. Okay, that's why these PID controllers are kind of quite powerful tools that are available in the market, and they work quite well. So in the presence of, even if we don't know whether the system is nonlinear or linear, or as long as it's a fully actuated mechanical system, there are no under actuations in the system, then this PD control is going to work quite well. Now the problem comes when we want to do the trajectory tracking. Okay, this trajectory tracking is an important issue here. So for that we need a lot more kind of a thing to be done. Okay, so the trajectory tracking problem is simply like this. Suppose you have a two-link manipulator, say just explained by using this two-link manipulator, but we want to track this trajectory, like say the problem is given that we want to go from PS to PF in 3 seconds along the along this path, okay, a straight line path. This becomes like a motion or path planning problem. Okay, and the solution to this path planning problem will give you theta 1 desired and theta 2 desired as a function of time, which will make this happen. So we first get this path trajectory kinematics done. Like, okay, if I know x position, I know what is the y position, and if I know x position in time, I know what is the y position in time. That is the kinematics of the path that is solved. Then I can convert that x of t and y of t into theta 1 of t and theta 2 of t. Okay, and then I get these are like my desired thetas, which will take me along that path. So I want to now track the trajectory for theta 1 to go along theta 1 desired as a function of time. Okay, so this is like a inverse kinematic problem. Okay, given end effector position in terms of time, how do I get my joint coordinates in terms of time? Okay, that's a motion or path planning problem that is typically used in robotics kind of literature. Okay, and similar kind of a thing exists for any mechatronic system. For example, if I want to go, if I want to have some desired kind of a operation done in time as a trajectory thing, then what should be my joint or my motor angles in terms of time? And once we know this theta 1 desired t and theta 2 desired t, or q1 desired t, q2 desired t, how do I now track this desired trajectory? Okay, that is a problem. So then computed torque controller is one of the ideas that can be used. So this computed torque is basically an idea where you know this trajectory, you know this joint angles based on the derivative now. So the joint angle desired are known, the desired joint angle derivatives will be known, and those one can use from this equation of dynamics. So this is the equation of dynamics here. You know this, say suppose joint angles q are known, their derivatives are known, q double dots are known, q dots are known. So everything here is known. Then you know what is a control that will without any other disturbances. You will know what is the desired control that is to be there, right? Because q, when I know the trajectory q, okay, I know q dot, q double dot. Okay, all are desired. Of course, they are desired. You put in this equation, and you will get to know what is the torque that will maintain those desired trajectory in the absence of any other disturbances. Okay, any other kind of so this is how you find that computed torque, and use that torque. In addition, you use that the control now should be that you desired plus this feedback u, or you feed forward and you feedback, and then this controller will work typically. Okay, so that's what is written here. Like analysis of computed torque controllers can be, then one can use this computed torque control and see whether we can use our Lyapunov theory to kind of get something from there. Okay. So the problem here is that Laplace theorem you will not be able to apply. So I would leave this analysis. You carry out this analysis, then some things will make sense. You do this computed torque based control and try to kind of see a similar kind of a PD control plus feed forward computed torque control term you can use as a control, and start working out Lyapunov analysis, and you will find that this Laplace theorem may not be applied in this case. Okay, so there are some other kind of a stability proofs that will be needed. Okay, so this is out of scope of this course. Okay, but there is a very high performance tracking controller that can be possible. Okay, this expression of this controller is given here. Okay, see these DC terms are coming from the system equation of dynamics that we have seen before, and these other terms are nu and a are defined in this manner here. Okay, this is called Lee-Slotin controller, and this is a controller. This can do the trajectory tracking also. See, this q desired is not constant here, it can be function of time also, and how this is able to kind of do the job we can prove by Lyapunov stability analysis. That will be happening in the future classes to come. Okay, but you can ponder over this controller and see whether you are able to kind of carry out the analysis of this by using Lyapunov theory, and this control is applied in the equation of this kind. Okay, so this u is basically given by that expression that you see as a tau expression in the control here. Okay, this expression. Okay, and gravity is not there here. Okay, again you assume that gravity is 0, g term is 0 in the equation of dynamics, and see whether you are able to kind of do something about proof of that. Okay, and the hint is like, you express everything in this variable r. Okay, and try to express everything in terms of variable r, although your generalized coordinates are q. Okay, you express everything in terms of r, and you will find some interesting thing happens in that coordinate dimension. Okay, so we will do that analysis in the future classes to come. Okay, thank you. We will stop here for now.